This video is for the key features of exponential growth and exponential decay functions. Alright, so the y-intercept is the y-coordinate of a point at which the relation crosses the y-axis. The y-intercept in an exponential function is represented by the a value. Okay? An asymptote is a line that is approached and may or may not be crossed. A horizontal asymptote is a horizontal line approached by the curve as the function approaches positive or negative infinity. So horizontal asymptotes may be crossed by the curve in these exponential functions, and it'll make more sense once you see it. So this first one here, we're going to identify the key attributes of the exponential function 2 times 1.5 to the x. So the first thing we're going to do is we are going to create a table and we are going to graph this function. So I'm going to go to y equals and do 2 times 1.5 to the x power. And then I'm going to go to table. Alright, so my first x value that I have is a negative 10. So negative 10, we've got 0.0347. And then we're going to go to negative 3, which is 0.5926. And then negative 1, looks like it's 1.3 repeating. And then 0 is a 2. Get a couple more values up there. 1 is a 3. 2 is a 4.5. 3 is a 6.75. And then 4 is 10.125. Okay, so once I've created a table, I can graph this function. Alright, so negative 10 is real close to 0. Negative 3 is close to, it's a little over half. Negative 1 is about 1 1/3. 0 is 2. 1 is 3. 2 is 4.5. 3, 6.75, and 4 is up here a little over 10. And so then we can connect the dots. And we've graphed that function. So the first question is, what is the y-intercept of the exponential function? So you can tell that by looking at this. The y-intercept is at 2. So we write it as an ordered pair, 0, 2. And it says, what is the horizontal asymptote? So the horizontal asymptote is this line here where that curve starts evening out. And so in this case, our function is never going to cross y equals 0. And so that is our horizontal asymptote. That's where it starts leveling off, and it's always going to just border that, but it's never going to cross that line y equals 0. Alright, the next one I have says a certain bacteria doubles every 20 minutes. A population sample that begins with 10 cells in the culture can be represented by the function f of x equals 10 times 2 to the x, where x is the time in 20-minute increments. So same deal here. We are going to create a table first. And we're starting at 0. So 0 is 10, 1 is 20, 2 is 40, 3 is 80. So you can see it's doubling every time. And then 4 is 160. Sorry, that's a little off. And so now we can graph it. So 0, 10, so that's our first point. 120, 2, 40, 3 goes all the way up here to 80, and then 4 is 160. So for this one, we're going to start at this point here. And so that's what my graph would look like. And so the reason that I didn't add an arrow over here is because X is representing time, and we can't have time less than 0. So my y-intercept again is going to be the a value. It's the number outside the parentheses, or where x is 0, or where your graph crosses the x-axis. So 0, 10. And then it says, what is the horizontal asymptote? So for this one, there is no horizontal asymptote in the problem situation because the initial amount of bacteria only increases as time increases. So what this means is it's only going to go up from 10. So this part of the graph that's over here in quadrant 4 is never going to happen. The amount of bacteria is never going to be less than 10. So it's not going to start bordering a line and always staying right next to it. Again, if we had to say, if we were just looking at the function without the real world situation attached to it, the horizontal asymptote would be the same at y equals 0. Okay, so decay is identical, okay? They just look a little bit different. So the first one here says identify the key attributes of the exponential function 200 times 0.5 to the x power, and we do the exact same thing. We go to y equals, we do 200 times 0.5 to the x power, and then we're going to look at the table. Alright, so at -4, y is 3200. At -3, it's 1600. At -2, it's 800. At -1, it's 400. So you can see it's being cut in half on this one. 0 is 200, and 1 is 100. So now I can graph it. So -4, go up to 3200. -3 goes up to 1600. -2 is 800. -1 is 400. 0 is 200. So you can see these are counting. Each line represents 200. And then 1 would be about there. So we can connect the dots. So our y-intercept, where the line crosses, where x is 0, or the number in front of parentheses. So here it's 0, 200, and then the horizontal asymptote is y equals 0. It's not going to cross that line. It's always just going to kind of border right on that line. All right, our last one, a powerful computer is purchased for $2,000, but loses 40% of its value each year and can be represented by the function f of x equals 2,000 times 0.6 to the x power. So again, same exact thing. Alright, so we're starting at 0 this time. I'm just getting all my numbers up there. Alright, so at 0, y is 2,000. And at 1, 1,200. 720, 432, 259.2, 155.52, 93.31, 55.99, 33.59, and 20.16. Okay, so now we can graph. So 0 is 2,000, 1 is 1,200, 2 is 720, so somewhere in there, 3 is 432, 4 55, 6, 7, 8, and 9. So you do have to guesstimate a little bit with these. And so now we can connect our dots. So again, with the real world situations, we graph them a little bit differently. So our y-intercept is 0, 2000. And then the horizontal asymptote is y equals 0. So the reason it's y equals 0 here, if you remember on the other page, it was never going to get less than 10. Okay, so that was a growth function. For decay, this line will start borderlining that y equals 0 line. So no matter how many years pass, the computer will still have some value.